Okay, so we're talking about the Lorentz transformation. In particular, I want to focus today on time dilation, or the fact that time is not absolute, the fact that you measure time differently in different reference frames. Moving clocks run slow. We got to figure out what that means because that is really misleading. So let's start with another one of these Gedanken experiments of Einstein's, and let's put Mary on the moving train. And let's put Frank on the stationary train. I think it was the other way around before. So this is Mary. Mary's got the small head. And this is Frank. Frank's got the big head. So let me just put an M for Mary and an F for Frank. Okay, so let's say that they're on two trains. And I want Mary's train to be moving at speed V. I don't know if you can see that. The V is on top of Mary. So let me go back and delete. Oh, crumbs. I'm just going to delete Mary. Sorry, Mary. Okay. Okay, let me try that again. So Mary's on the moving train. Frank's on the stationary train. Mary's just invisible or something. She's got a superpower. And so I want to know, we can use the Lorentz transformation, but we need to use a little bit of physics too to figure out if Mary measures a certain time and she says, and she knows she's gone a certain distance, what distance and time do Frank measure? So let's just be really careful here, right, with reference frames. So Mary is the moving reference frame O prime. Frank is the stationary reference frame O. And Mary's coordinate axis, X prime and Y prime, they travel with her. Frank's coordinate axis, he's stationary. He's just parked in the station, and his stays with him. So at a later time, Mary is, right, she's over here, let's say. She's rolled down the tracks. And what's important to recognize is that her reference frame still moves with her. We're going to talk about something which I don't think we've seen before, which is pretty straightforward, really. Okay, so her reference frame moves with her. So the question is what does Mary measure for a time, and what does Mary measure for a distance, according to her coordinate reference frame? So how far has Mary moved relative to her coordinate reference frame? That's delta x prime. And how much time did it take Mary to go from her initial position shown on the left to her final position shown on the right? So first of all, let's define her time and just say, oh, her time is however long it took her, and we're going to call that t sub 0. We're gonna later on we're gonna rename that the proper time, but don't worry about that right now. We're gonna call that t sub 0, just the time measured by Mary. But what's the distance measured by Mary? The distance measured, not how far does she know she's gone, but what is the distance measured by her frame of reference? Her frame of reference, relative to her frame of reference, the train is at the origin on the left. She's moved down the track. She carries her frame of reference with her. The train is still at the origin. What is Mary's distance according to delta x prime? It's 0. Right? She doesn't move relative to her own frame of reference. You do not move relative to your own frame of reference. We did actually mention that one time before. That's an important point where we may be looking at two different distances, delta x prime and delta x, from some other reference frame. But if you're in the reference frame, you're carrying your coordinate axis with you, and you do not move relative to your own coordinate axis. So Mary's distance is delta x prime equals 0, and Mary's time is just some arbitrary time. I'm just going to give it the name t0 because we're going to see later that it's a special time. So then we want to ask how, so that's just defining our variables, starting by defining our variables. So then we want to ask, how much time does Frank measure? Frank, we know from previous discussion, is going to measure a different time because he's in a different inertial frame. But in order to figure out how much time Frank measures, we need to know how much distance does Frank measure. So how much distance does Frank measure? Well, Frank measures a time delta t, whatever that is. It's going to be different than delta t prime. And how much distance does Frank measure? Well, there's a couple of ways you can get at that distance. One is we can use the Lorentz transformation, and we will in a second, to figure out that distance. But actually, It's easy enough for Frank to say Mary is moving at v relative to him, right? I mean, that's an absolute. V is the relative velocity. So if Mary is moving at v relative to him, and she's moving at a constant velocity, then Frank knows distance equals rate times time. So according to Frank, if Mary moves for a time delta t, what is delta x? You should be able to do this. It's constant velocity kinematics, right? Delta x equals v delta t. Okay, so delta t is an unknown right now. We just want to say, oh, Frank measures a delta t, whatever that is. What we're going to do is relate that delta t to delta t prime in a second, which we're calling t0, but delta t to delta t prime. Okay, so, but we know that delta x is v delta t. Now, let's write down the Lorentz transformation formulas. So there's the Lorentz transformation formulas, right? That's the Lorentz transformation to go from the unprime frame to the prime frame for delta x and delta t. Delta x prime to delta t prime. Now, first of all, you can see from the first Lorentz transformation equation, now that we have defined our variables, delta t prime is t0, delta x prime is 0, delta x is v delta t is an unknown. Delta t prime is an unknown too, but really what we want to look for is if delta t prime is fixed, what is delta t? Okay, so we know our four variables. We can go ahead and plug in to Lorentz transformation. So we can go ahead and plug into the Lorentz transformation. Notice what happens if we plug into the first of the Lorentz transformation equations. Plug into the first of the Lorentz transformation equations, and you get, if you plug in delta x prime equals 0, you simply get delta x equals v delta t. Oh, okay, that's what we knew by kinematics, right? So we also know that by Lorentz transformation. Lorentz transformation is nothing magic here. It's just an equation, which gives us the relationship. Okay. So what about the second Lorentz transformation equation? That's going to allow us to relate delta t prime to delta t. So we can go ahead and plug in for what's known, right? Delta t prime is t0. And so what I've done is just divided both sides by gamma and plugged in delta x because that's also known as v delta t, right? So now I've got this equation here, which I plugged in the variables that we have identified as known, and now let's figure out what the relationship is between delta t and delta t prime. Now remember, I just replaced delta t prime with t0. I probably did that too early. I should have done it later. Should have just called that delta t prime. Let's go ahead and do that. So just saying there's nothing magic about delta t prime equals t0. I just went back in and said, what's the relationship between delta t and delta t prime? Okay, that's what we're getting from the second Lorentz transformation equation. Okay, so here I just rewrite the equation that we had from the other page, the second of the Galilean transformation equations, written in terms to try to find the relationship between delta t and delta t prime. And what I want you to notice is you can factor out a delta t on the right? This is algebra. You got to just mess with the algebra. And you see that you get a 1 minus v squared over c squared. Ah, that looks familiar. That is actually 1 over gamma squared, right? So a gamma is the square root of that inverted. So that's 1 over gamma squared. Oops, not a t0 here, a delta t prime. Let's come back to this. Not a t0 here. This is still, we just decided to not call that t0 yet. This is still delta. Give me a pen. Delta t prime. And so what we find is delta t prime over gamma is delta t over gamma squared. Okay, so that gives us delta t equals gamma delta t prime. Okay, the end. All right, so we have now found, let's go back to the previous page. How do I do that? There we go. We have now found from that we had, if we have a certain delta t prime measured in the frame of reference in which the axis moves with the frame, right? Delta x prime equals 0 and delta t prime is measured. We wanted to find the relationship between delta t and delta t prime, and we have done that here. Whoops. And okay, so delta t equals gamma delta t prime. So first thing to notice is that we're simply showing that you're measuring a different time in Mary's reference frame and Frank's reference frame, right? So Mary is measuring this time and Frank is measuring this time. Okay, Great. They measure a different time, and it's a real time. It's going to be a time measured on their watch. It's going to be their bodies are actually aging. Frank's body is aging at a different rate than Mary's body. And so what can you say about the relationship between delta t and delta t prime? Notice that, what can you say about gamma, right? So again, it comes back to what is the range of gamma? Well, we know that gamma is greater than or equal to 1. So what can you say about delta t versus delta t prime? Right? You can say that that delta t, again, t0, delta t prime, that delta t must be greater than or equal to delta t prime, since gamma is greater than or equal to 1. So who measures the shortest time? In which reference frame is the shortest time measured? There is a shortest time measured in a reference frame. And whose reference frame is that? Mary is always going to measure the shortest time. No matter how fast or slow Frank moves relative to Mary, Mary's going to measure the shortest time. So what is special about Mary's frame? What's special about Mary's frame is that she's the frame in which delta x prime is equal to 0. So really, the shortest time is measured in the frame in which delta x prime is equal to 0. And again, think physics, not arbitrary, this isn't just a mathematical result. Think physics. What does it mean for delta x prime equals 0? It literally means that Mary is watching her watch. She can look at her watch when she leaves the first station, and she can look at her watch when she reaches the second station, and she can say, okay, the time that I'm measuring is shorter than the time that Frank's measuring, and the reason why is because delta x prime is equal to 0. The reason why is because my watch was present at both events. That's what's important, is that her watch didn't move relative to her origin. It was present at both events. Frank's watch is not present at both events. Frank was present when Mary left the first station, but Frank is not at the second station. So who measures the shortest time? Is the person who carries the watch, or the person who has a watch that is present at both events. Now, it may be that there's a situation where nobody has a watch present at both events, in which case I don't know which one's shorter. But the shortest possible time measured is the time measured by the watch that is present at the two events that are where we're measuring the time between them. So if there's any two events, we're measuring the time between them. If the watch is present at the first event and the second event, that watch is going to measure the shortest time. And so that's a special time that we call proper time. And we give it the letter T0, hence that's why I gave it the letter to begin with. So now everywhere we can say, oh, okay, Mary measures the proper time because she's got the watch present at her starting at the left station and ending at the right station. And Frank is going to measure a longer time. It doesn't matter how fast he moves, doesn't matter where he is, he's going to measure a longer time, unless he travels with Mary, in which case he's then measuring the shortest time. Okay, so what does this mean? What do I mean by what does that mean? I mean, what does this mean in terms of those initial statements, right? So again, T0 is the shortest time. Yeah, okay. So those initial statements, let's go back to our initial statements. Time is not absolute. First of all, we know that if you're in different inertial reference frames, you measure actual different times. Moving clocks run slow. Mary is measuring the shortest time. We think of that as it shows, so time is going the slowest for her. Mary, who has the clock that is moving from station 1, let's call that Lynchburg, to station 2, let's call that New Orleans. She's going to New Orleans. She's got the clock that's present at both events. Her clock moved, so her clock ran slow. The reason why moving clocks run slow is in quotes, and that you should probably not use that, is because it doesn't really make sense in a lot of contexts. And the fact, what it really should say is the clock present at both events runs slow, not moving clocks run slow, because let's say that we made Mary the stationary reference frame and Frank the moving reference frame. But I mean, we could just call Mary the frame O and Frank the frame O prime, and still have Mary be the one, and still have Mary go from Lynchburg to New Orleans, but have Frank moving backwards at speed v. But Mary's still measuring the shortest time because she's the one who has the clock at both those events. So moving clocks run slow doesn't mean that every moving clock runs slower than every other moving clock, because all clocks move relative to each other. Time dilation. What does time dilation mean? Time can be shorter, can be dilated, can be longer. Is that the opposite of dilation? But time dilation just means time is not absolute, that it is measured at different amounts in different frames of reference. Okay, so there you go. That's time dilation. That's also proper time. It's also just another example of using Lorentz transformation formula. I do want to just take a little time in the next lecture to talk about this concept of time dilation from a very physical point of view.